I'm excited to introduce Aleksander Molak from the University of Oxford and Causal Python IO. Aleksander is a Causal ML tutor and a host of the Causal Bandits podcast, which is often the entertainment on my morning commute. So thank you very much. Alex will be presenting on causality upside down, which promises to challenge our thinking and provide new perspectives on causal inference. Please welcome Aleksander.
Welcome to the strange world of causality. A strange thing to say after so many talks about causality. When we first learn about causality, we often hear a lot about assumptions. And there's a very good reason for that, because assumptions are very important in causality. The reason for that is that the information about the data generating process is in general not contained in the observations, in the data that we observe. Even in interventions, the amount of causal information is incomplete from the point of view of counterfactuals. And so our assumptions help us to make sure that the external information that is not coming from the data, that we can use it in a useful way. And by useful, I mean in a way that helps us achieve our goals, which very often is answering some kinds of questions. Questions about something we don't yet know. But perhaps sometimes we can focus on assumptions a little bit too much. And when this happens, we might lose the forest for the trees, so to say. There's also another danger in focusing on assumptions too much. In particular, when we focus on them through biased lens. And this can lead us to very compelling illusions, producing very compelling illusions for ourselves. A good example of this is this, not exact, but a quote from a causal practitioner from a major organization who said, "The SCM, structural causal modeling framework, does not work in practice because it requires too many assumptions, too restrictive assumptions. And that's why we only use potential outcomes." The problem with this thinking is that the structural causal model framework and potential outcomes frameworks are logically equivalent, largely logically equivalent. The consequence of this is that if we violate an assumption in the structural causal model framework, we are also in trouble in the potential outcomes framework. But sometimes it might become invisible for us. The reason for this is that in different literature streams, we have different narratives about assumptions. People are using different languages. And they also put emphasis differently. And these differences in emphasis can lead us to an illusion that if we use certain methods, then we can escape, in a sense, the assumptions that sometimes, for some of us, seem to be restrictive or too restrictive. One good example of this is using so-called quasi-experimental methods, like synthetic control or difference in differences, and so on and so on. For some practitioners, you will hear from some practitioners in industry that they believe that if we use these methods, if we can use these methods, our data allows us to use these methods, we essentially get causal identification out of the box. But this, unfortunately, is not true. I described one case of how this can be misleading in the last part of this blog post that I wrote some time ago. And I started talking about assumptions, but I haven't introduced myself. My name is Alex, and I help companies streamline their causal journeys through workshops and consulting. And I also wrote this book some time ago called Causal Inference and Discovery in Python. And a fun fact about this book is that it outsold Harry Potter on Amazon in terms of weekly sales, and only for 1 week. But it makes a good case for us. I know that here in the audience is at least one person that is also thinking about writing a book. And for every person who is writing a book, and if they, assuming they care about their audience, sales will be important. So we can imagine that this person writes a book and they release it and they observe sales over time. And they're interested in an effect of an influencer publishing a post about their book. To quantify the effect of this post by an influencer, we need to simulate what would the reality be if there was no post by an influencer. So we can produce something like this: a predicted counterfactual sales time series. Maybe we have some data. We put this data in the model, and the model says, "Hey, if everything was normal, no influencer posts, no this particular influencer post existing, the sales would be like this." That's our best estimation. And then we say, okay, the influencer post was here, so now we can compare those two graphs, and we can get this thing, which would be our causal effect of the influencers post. So this method is called synthetic control, or one possible variant of synthetic control estimator. But there's one challenge here. The challenge is that we can, by using this method, produce an illusion. If we don't think about assumptions carefully, we can fall into the trap of thinking that this is a valid conclusion, our quantification of the causal method is valid, but there might be another event that happened that we don't know of that inspired the influencer to post and at the same time inspired people to buy, aka a hidden confounder. So although we are using a quasi-experimental method, hidden confounding still can be a problem for us here. And so we don't have causal identification. We don't get causal identification for free here. So for many people using quasi-experimental methods, when they see this, they say, oh, so what can we do? Is there anything we can do? And if we think about this in binary terms, we just say, hey, if the assumption is not met, conclusions are not valid. If assumption B is not met, causal inference impossible. If we think this way, there's not much left for us. We're done, and the question seems to be fundamentally unanswerable. But there's another perspective we can take here, and we can think about assumptions as a spectrum, rather than thinking about them in binary terms. And this opens the door for creativity for us. So for instance, when you think about quasi-experimental methods like synthetic control that we've seen a second ago, most people will think about these methods, somehow they will have a separate drawer in their brain as compared to using graphs or DAGs, causal graphs that you've seen some of them today. But you can actually combine them, and there's nothing that stops you from combining them. So this comes from a paper co-authored by our Spotify speakers today. And this is a causal graph that was produced to help the analysis for synthetic control estimator. It might seem non-traditional for some of us, but it is honest. It is honest in a sense that in this graph, we encode all the knowledge that we have. So we know certain things, and we say, okay, these are things according to us today, honestly, the best we know of today. And when we do this, maybe we can go somewhere and look for methods that allow us to do something with our problem, even if there is hidden confounding. But this allows us to be courageous, to have courage, to admit in front of ourselves that there are things we don't know as well, and maybe we cannot learn about them. If we have this courage, we can get creative, and we can start looking for solutions that can help us answer our question in a way that might not be perfect, but might be useful. So this is the paper where I took the figures from. The first author is Jacob Zeitler, and the two other authors you were able to hear from them today, Athanasios and Kieran, who's sitting here. Both talks I really loved. And so these three elements, honesty, courage, and creativity, open the doors for us to do much more with causality than we could initially think when we just read some introductory materials. And if this perspective sounds interesting to you, we also have this podcast episode with Jacob, the first author of that paper, when we talk about the cost of causal assumptions and what can we do and how can we think about assumptions in a more creative, more open way sometimes. And now I want to share with you just a couple of papers that I think are great examples of thinking in a way that goes beyond the traditional limitations that we have in literature. And I will briefly explain to you or share with you what those papers are doing. So the first one is this paper from Dennis Frauen and colleagues. These are researchers from LMU, from Munich, and also Michaela van der Schaar and Alicia Kurf from Cambridge. It's a neural framework for generalized causal sensitivity analysis. Sensitivity analysis is this thing where we say, okay, maybe there's a hidden confounding, we cannot observe it. But maybe we can say something about the causal effect. And maybe we can say the causal effect, given our assumptions about the hidden confounder, the most reasonable assumptions we can make, the causal effect will be between 3 and 10. If we change the treatment, maybe the causal effect will be between -5 and 2. If we know this, we can pick the treatment that is better. So that might be enough for us to make a useful decision, even if we don't have causal identifiability per se. And you can see what is important about this paper is that sensitivity model, we have a whole zoo of sensitivity models that are applicable for very, very special cases. And so it might be very difficult for instance, for your team, if you're in industry, to learn about all of them and really practice with them and so on and so on. So this paper proposes a framework that generalizes a number of those sensitivity frameworks and allows us to apply one device to different kinds of queries and different kinds of circumstances. In this paper, the authors talk about another interesting problem. So probably most of you who are in machine learning heard about this thing about learning a representation. So for instance, when we have a transformer like ChatGPT, it will learn some internal representation of the data. It's compressed data, it compresses the data. And this learned representation is compact, and it allows us to generate predictions or sometimes generate tokens, for instance. But it turns out that when we use a model like this in the causal setting, learning this representation might actually introduce additional confounding. So there might be no confounding in the data, but there might be new confounding, new type of confounding appearing in the representation learned by the model. So the method described in this paper allows us to put bounds, again, some range of values on this hidden confounding, on this representation-induced confounding. So that was about everything we said so far was about the second rung of the Pearl's ladder of causation, about interventional stuff, where we are interested in the treatment, the effect of the treatment or something. But we can also do something creative and useful on the third rank. The third rank, counterfactual rank, is often, and in my opinion rightfully so, treated as the most demanding, the most difficult to talk about and to model. So in this work, series of papers by Judea Pearl and Scott Muller, they work on showing us that we can use observational and interventional data together, combining them, in order to say something useful about counterfactuals. This might be very useful in personalized medicine, but also in anything related to marketing. So we can say something about particular individuals, not very precisely, but sometimes precisely enough that it allows us to make an optimal decision. But that's also not all. We can also be creative in causal discovery. Causal discovery is also seen by many as a very, very challenging topic because we are trying to learn the causal structure from the data that we are observing and sometimes data on interventions. And we can actually say that without additional assumptions, causal discovery is impossible. So in this paper, Siwan Guo and colleagues proposed a model that allows us to recover causal structure in a setting where the data is not IID. IID stands for independent and identically distributed. We usually in statistics love data that is IID because it makes everything easier. And this is all the generalization that we have in machine learning today is based on the IID assumption. If we go outside of the IID data, virtually all most popular machine learning models will collapse. They will not generalize. They cannot do it. But here, we can actually leverage the fact that the data is not IID, but is exchangeable. We won't talk about this in detail because it would take a lot of time. But the data that is exchangeable, but not IID, and we can leverage this fact because it introduces a kind of asymmetry in the data to recover the causal structure. A more intuitive view on this would be that maybe we have patients in different regions of the world, or we have patients in different hospitals. The mechanics, the dynamics of the disease is the same in every hospital or in every country, but there are different procedures in different countries or different hospitals. And these differences in procedures will allow us to look at the data and find out what is not changing there, what is constant between those cases. So that's a general intuition about this. In this paper from Shohei Shimizu, he's the creator of a causal discovery method, for those of you who are familiar with this, called Lingam, and Takashi Maeda. They propose a method where we can use prior knowledge, something we know about our data, in time series when we have unobserved confounders and recover causal structure. So in causality, most of you who are familiar with those topics, you will know that hidden confounding, it's a bad thing. But here actually, they overcome this limitation. Again, it requires certain assumptions, but you can see that their method, the blue one, outperforms a number of traditional or classical methods for causal discovery from time series, including a variant of the PC algorithm and a variant of the Lingam algorithm. The next one, I think, is very interesting, and it's shocking for many people who learned causality through a very traditional path. And it's called learning to induce causal structure. It sounds very enigmatic, but what this paper says is basically that perhaps instead of thinking about causal discovery as an unsupervised task, when the model only looks at the data and is trying to find something in the data, some signal in the data, we actually train a model in a supervised way. Supervised way, which means, hey, this is a graph, this is the data, this is the causal structure. We simulate some data, we train a model like this, and it learns something. And it turns out that the results are surprisingly good. So here, the method proposed is the blue one. The lower the bar, the better the model. Here you have DCDI and ENCODE. These are other causal discovery methods. And you can see that it performs uniformly better than those methods. These are pretty advanced methods. If they're optimal for those types of graphs, well, that's another question, but we can see here. Many researchers after this paper were shocked that supervised causal discovery can work so well. And people started thinking, okay, so we have all this causal theory from Pearl and so on and so on. And here we have a supervised model, we have a transformer model, and it's just better than anything. It violates the theory somehow. It turns out there's a very interesting recent paper from Francesco Montagna's group that shows that this approach does not violate causal theory, and there are some limitations to it. But nevertheless, this approach can be very, very useful in a broad set of cases. And this is all just a small subset of what is really possible. A selection of papers that I thought might be interesting for our audience here today, and hopefully it was, at least for some of you. And the key takeaway from today is that indeed assumptions are very, very important in causality. But perhaps we will be better off if we treat them as a starting line rather than a finish line. And perhaps this can help us learn something new, because we ask causal questions to learn something that we don't yet know. And I believe that honesty, courage, and creativity can help us become true explorers, true discoverers. And I want to finish this talk today with one of my favorite quotes by Yuval Noah Harari. And I think this quote will resonate in a special way in this place where we are today in the ruralized society. The big revolution which launched modern science was discovery of ignorance. For thousands of years, people thought they know everything. Science began when some humans admitted we don't know everything. Now, when we have courage to admit our ignorance, we can start investigating. And that's science. Thank you.
Thank you, Alex. That was brilliant. Thank you.
Thank you so much.
I'm going to start with a really easy question.
We'll see.
Yeah, wait till I've read it. Given your extensive oversight of causal AI, where do you think we'll be with causal AI in 5 years' time?
Well, I cannot know this, but I think that the biggest opportunity for us as a causal community lies in building models that allow us to answer questions in a way that is maybe not as precise as we would wish in the ideal world, but models that require less of human curation at least some stages, and lead to decisions that are good enough to justify them.
And we will see, won't we? Huh? And we will see.
We will see if that's the case, of course.
Of course. I'm reading the question, not mean, but you're quite in favour of structural causal models and potential outcomes. Could you share a few things that practitioners should care about when using SCMs?
Well, I don't think that any of those frameworks, that one is better than another. But I think it's good to think clearly about stuff. And I believe that using graphs allows us to very clearly state our assumptions. So I had a conversation with Judea Pearl some time ago, and he told me, nobody thinks in conditional ignorability. And I think that's true. So it's very difficult to think clearly about causality when we think about very, hard to grasp concepts. And we had this beautiful talk before my talk about communication. And I think DAGs also give us a great device to communicate clearly with stakeholders and anyone who is involved in a causal project, even if they are not technical people. And I've seen this repeatedly in organizations, helping them move forward. In general, when using SCMs, if you decide to use the SCM framework, well, I think you need to remember about the assumptions if you want to make good decisions, but also be creative with them. And I think someone said this today before, sometimes starting small is the best way to move forward. Just starting with a subset of a problem, of a larger problem we want to solve, and build from there. So that's a little bit general, but I hope that will be helpful.
Very helpful. There was actually another question very similar, which was sensitivity analysis is great, but it's difficult to communicate this with business stakeholders. Do you have any tips? I think you've had a few there, but anything specifically about sensitivity analysis?
Well, I think what I found works pretty good is to start, before we start talking about sensitivity analysis and using all those cryptic words for, cryptic for people who are outside of the technical realm, I think it's good to frame things in terms of making a decision. And we can say, okay, we cannot say what is the exact causal effect here, but for our decision, it's clear from our analysis that this decision will be better. The effect will be probably between 3 and 4.5. We don't know. We cannot say today. I mean, we can pretend that we know, but we don't know really. But this is the positive effect that we expect from this decision. From the other, if we make the decision the other way around, the effect will be between 1 and 2. And I think that should be pretty clear for most people. At least in my experience, it worked pretty well. So starting with thinking in terms of a decision that we want to make, rather than from the technical point of view.
And get buy-in around that, what you're trying to do. Yeah, excellent, thank you. I'm going to pull a couple of questions together that are basically asking about how to learn and get started on causal modeling. One of them is, for someone fairly new to causal modeling, how do you shorten the path to using it competently? And then the second one, what is currently the best technical online course on causal AI with a study of about 140 hours, so more advanced? So a general question on how to plan. You are allowed to reference podcasts, just saying.
Yeah. So what's the best way to start? I personally believe that a great way to start is to read The Book of Why by Judea Pearl. Then if you want to understand the mathematics behind causal reasoning, but not go too deep into like Python and stuff, there's this book called The Primer. So Judea Pearl, when I was learning this, I was lucky enough, I just tagged him on Twitter and I asked, hey, I've read The Book of Why, I loved it. What's next? Which book should I read next? What do you think? And he replied. So he said The Primer. I had no idea about The Primer. I bought The Primer. I read The Primer. It was a great choice. So I think that's a great thing. There's also another book, if you want to get another perspective and you don't want to invest too much time, there's a great book by Paul Rosenbaum called Causal Inference. It's a small book. It gives another perspective, more from potential outcome, Fisherian point of view, and so on. So these 3 books, I think, would be a great start. And if you want to go in something more technical, specifically in Python, I wrote my book keeping in mind a person like this, right, who read The Book of Why and they want to start coding in Python. Another book in Python is from Mateusz Fakuri, who is also giving a virtual talk today, which is more from the econometrics point of view. Mine is more from machine learning point of view, I would say. So I think whatever works for you better.
Excellent.
The online course, well, I don't know. I mean, there's Robert Ness has a course which has a very interesting perspective, and there's a new course as well on Udemy. But I don't know. I haven't taken it, so I don't really know how good it is. Brady Neal on YouTube. On YouTube there's a free course by Brady Neal, and I'll be releasing my free course in some time as well. So, yeah, stay tuned.
Stay tuned. Right. One last question, then we're going to wrap up. But You'll be around for drinks, I'm sure, so people can catch you if they
Yes,
want
yes,
to.
I'll be
Bubbling?
around. I'm staying here. Yeah.
Yeah. Okay, so how do you know when you've included sufficient complexity into a causal model?
Oh, that's an excellent question, but it's very difficult to answer without understanding the problem. I think we always make those contextual decisions, and it's good. I think we should make contextual decisions because this is what differentiates a good analysis or good modeling from something very generic. Sufficient complexity, in very general terms, I would say sufficient complexity is the level of complexity that allows us to pick which decision is better. Because at the end of the day, we are all here to solve real problems. We are not here to, theory is super interesting, right? But at the end of the day, if we are in industry, we want to solve a problem, we want to answer a question, we want to learn something more. So whatever the complexity that allows us to make a decision is enough complexity, I would say.
Thank you, Alex. Thank you for anchoring us as well. Much appreciated.
Great. Thank you so much.